let's talk about the product rule. Here I've denoted capital F of x as our parent function, and that's going to equal the product of two smaller functions, or not necessarily smaller, but two other functions. We have f of x and g of x, lowercase for both of those. And we're trying to figure out what the derivative of this expression might be. As a first step, we always are going to divert to first principles and go to our limit definition. So f prime of x, we know from our limit definition, is going to equal the limit as h approaches 0 of what would be in the numerator. We would have f of x plus h, which in this case is lowercase f of x plus h, g of x plus h, minus lowercase f of x times g of x over h. And similar to when we were negotiating the chain rule, this is a perplexing position to be in. It's not immediately obvious how to deal with this, how to move forward. There's no common factor here. These are four independent factors. There's nothing we can pull out. And so we're going to have to introduce something. And the mechanism by which we're going to do that for the product rule is going to look something like this. We're going to try to introduce a constant here in the numerator, g of x plus h. If we were to add some constant and subtract by that same constant, this is not going to change the value of what we have going on here. And so if we can think of an appropriate constant that would allow us to negotiate this numerator and make some generalizations, we'll have some way to move forward. In order to do that, I'm actually going to flip the signs of these expressions here. I'm going to try to, in order to make this a little bit easier to pinpoint. And once again, although it's maybe not immediately obvious, what I'm noticing here is that if we're subtracting a constant here, if there was some way I could introduce g of x here, but I was able to factor out this f of x plus h, then I could potentially have here g of x plus h minus g of x. All of this is being divided by h, and we have the limit as h approaches 0. Well, that's just our formal definition for the derivative of g of x. And similarly here, if I was able to introduce some expression wherein I could pull out a g of x, but also introduce an f of x plus h, then here I could get f of x plus h minus f of x, all of that being divided by h, the limit as h approaches 0. Once again, that's our formal definition of the derivative for f of x. So if I could introduce some factor that has f of x plus h in g of x, then I think we might be in business here, and we could work in terms that would allow us to simplify this. And you might be thinking, well, what sort of term would have a factor of f of x plus h and g of x? Well, let me propose that for our constant here, we just say that it's equal to f of x plus h times g of x. And then if we're able to introduce that into our equation, let's say that this would be the limit as h approaches 0, f of x plus h times g of x plus h. All of this is staying the same. And then here we're going to add in our constant. I'll color it in some color. And once again, all we're doing is subtracting this constant, f of x plus h times g of x. And then we're going to add it, which in effect would cancel it, wouldn't change the value of this expression. So we're going to add this here, x plus h times g of x. Go back to my native color, subtract f of x times g of x. This once again is staying the same. And now once again, we're going to move forward as we postulated. The limit as h approaches 0. Here we can pull out that f of x plus h. This is just going to be f of x plus h times, and then I'm actually going to write this a little bit differently. I'm just going to separate this for reasons that will become apparent. G of x plus h minus g of x, all of this over h. And then what would we have here? Well, we would be adding, and we could pull out the g of x here. So we would pull out a g of x, and then what would be left? We would be multiplying by f of x plus h minus f of x over h. So this would be times f of x plus h minus f of x over h. The limit of this entire expression as h approaches 0. And you might have saw in my video on limit properties that the sum of the limit of two expressions is the same as the limit of the sum of those expressions. And similarly, once we have broken it up across these two things that are being added together, the product of two limits is going to be the same as the product of those limits. So in effect, to use some layman's terminology, you're essentially distributing this limit across all four of these expressions. And so what's the limit of f of x plus h as h approaches 0? Well, that's just f of x. And what's the limit of this expression as h approaches 0? That's just our formal definition of the derivative. So this is just going to be g prime of x. And then here we're just adding g of x. That's going to be changed by the limit. And then here, f of x plus h minus f of x over h, the limit as h approaches 0 of that is our formal expression for the derivative of f of x. So here we have discovered a way to take the derivative of two functions that are being multiplied together. So now let's move forward. As an example, we can verify the derivative of x to the power 4 via the product rule just to check to make sure this works. And so in a previous video, we demonstrated that if x is to the power of n, if this is the function we're dealing with, then the derivative of this is going to equal n times x to the power of n minus 1. And so in this case, the derivative of x to the power 4 with respect to x would equal 4 times x to the power of 3. Just dropping that power by 1 and bringing that out front, the power. And so how could we verify this via the product rule? Well, x to the power of 4 is just equal to x squared times x squared. And so if we know that if f of x is equal to some function times some other function, that the derivative of this is going to be f prime of x g of x plus g prime of x f of x, then we can use that to verify this. So what would the derivative of this be? Well, it would be the derivative of the first times the second. So what's the derivative of this? This would be 2x times x squared. Well, it's just 2x to the third, plus the derivative of the second, it's also 2x, times the first, x squared. So this is plus 2x cubed. And so we would get 4x cubed, and these do agree, which is great. So moving forward, let's talk about the quotient rule. This is going to be similar to the product rule, but rather than dealing with the product of two functions, we're just going to be dealing with situations wherein we have one function being divided by another. And we want to see similarly if we could find some sort of general rule that allows us to differentiate functions that show up in this format. You could think, for example, the function tangent of x is really just equal to sine of x over cosine of x. And so without even thinking about tangent of x, if we had the ability to differentiate sine of x and cosine of x, and we had this ability to deal with taking the derivative of two functions wherein one is being divided by the other, then we would be able to find the derivative of tangent of x without much hassle. And so a tool like this is going to be pretty useful, just like the product rule. And you might notice that this is really just the same thing as f of x times 1 over g of x. And so we can actually use the product rule here, which we just derived, and we could say that f prime of x, and we really don't even need to go back to our limit definition of a derivative. We could just use the product rule here, and we could see that this is going to be f prime of x times the second function itself, which is just 1 over g of x. And then we're going to be adding the first function multiplied by the derivative of the second. Once again, if we are not saying where that's coming from, that is literally just the application of this right here, the product rule. And so if we are multiplying by the derivative of the second, this is just going to be f of x times the derivative of 1 over g of x. That's just g of x to the power of -1. And so this would give us our answer, but I would argue we can actually simplify this a little bit further, because g of x to the power of -1, this seems like a situation wherein we can use our friend from the previous video, the chain rule, right? The chain rule tells us that in a situation where we have a function like f of g of x, the derivative of this is just going to be f prime evaluated at g of x multiplied by the derivative of g of x, g prime of x. This is our chain rule, and I would say we could use this here because this is a situation where our parent function, so to speak, this f function on the outside, would be x to the power of -1, and the function on the inside would be g of x, and so this would just be the derivative of x to the power of -1 evaluated at g of x, in this case, multiplied by the derivative of g of x, and we can figure that out. And so let's do that in a different color here, and let's say that the derivative, that's a very sloppy d, the derivative of g of x to the power of -1 with respect to x, this would equal, well, what's the derivative of x to the power of -1? That's just going to be -1 multiplied by x to the power of -2, just dropping down that exponent and decreasing the power by 1. That's just from our power rule. And so this is going to be -1 over g of x squared over g of x squared. And then we just need to multiply by the derivative of the inside, which in this case is just going to be g prime of x. And so all of this is going to be equal to -g prime of x divided by g of x squared. And now that we've evaluated this expression here is actually just equal to this one here, the rest is just simple algebra. In plugging this in, we just need to find a common denominator. If we're going to have g of x squared over here, we're going to have f of x times g prime of x, or negative g prime of x over g of x squared, and we want a g of x squared in the denominator here. We could just multiply the top and bottom by g of x, and we're going to get f prime of x times g of x divided by g of x squared. This is going to be our common denominator. And then we're going to subtract. What would we have here? We would have f of x being multiplied by g prime of x. I brought that negative out front, so f of x times g prime of x. And this is known as the quotient rule. So I want to reiterate that what we're actually doing here in differential calculus is we're coming up with these rules. We have the chain rule, the quotient rule, the product rule that we derived in this video and the last one. And all of these are abstractions. They're generalizations that allow us to identify certain patterns, such as this one, f of g of x, or this one, f of x over g of x. When we're in, we can identify functions that appear in this sort of situation, and then we have the tools to differentiate those more quickly than if we were having to divert to first principles every single time that we wanted to do that. That is going to be the crux of the first part of differential calculus. We're coming up with these rules that allow us as students, as mathematicians, to take derivatives more quickly. And we're doing that through the use of these abstractions. They allow us to identify these patterns and come to an answer more quickly. But I just want to emphasize, and I'm going to use the function, the square root of x, in order to do this, that you don't have to do that. There's two options that we could take the derivative here. We can go back to first principles, which would be our definition of a derivative, right? So in this case, f prime of x would be equal to the limit, as h approaches 0, of the square root of x plus h minus the square root of x divided by h. This is our formal definition of a derivative, and we can evaluate this, right? We could multiply by the conjugate. We can multiply by the square root of x plus h plus the square root of x, and you might recognize this as the difference of two squares, so to speak, but just in unfactorized form. And we can multiply the top and bottom by this. It doesn't change the value of the function. On the top here, we're going to have the first factor squared minus the second factor squared, which is just going to be square root of x plus h squared minus the square root of x squared, which you might quickly recognize is just going to be h, because you'd have x plus h minus x, which is going to be h. Then on the bottom here, we would have h being multiplied by the square root of x plus h plus the square root of x. These h's would cancel. We'd be left with 1 over the square root of x plus h plus the square root of x. Forgetting this, but we'd have the limit as h approaches 0. And now we don't have this problem in our denominator that we had in the original unsimplified, or I guess this isn't more simple, but the original derivative definition. We don't have this divide by 0 error. Now we could just plug in 0 here. This is going to be 1 over, when at the limit as h approaches 0 here would be 1 over the square root of x plus the square root of x, which is just equal to 1 over 2 times the square root of x. Alternatively, we could recognize using the power rule, that this is just equal to x to the power of 1/2, and the derivative of this is just going to equal 1/2 multiplied by you take this exponent out front and then you decrease it by a power of 1. That's going to be x to the power of negative 1/2, which is just 1 over the square root of x, multiplied by 1/2, that's 1 over 2 square root of x. And so you can see that with these abstractions, with these rules, with these laws of differential calculus, we're able to come to the same answer much more quickly than we would if we had to divert to first principles every time we wanted to solve a problem. But I just want to emphasize that this is always an option, and very frequently when posed with a challenging derivative, when posed with a challenging integral, which is a concept we're going to get into later, sometimes it helps to divert to first principles and remind ourselves what we are really doing when we're taking these derivatives. I don't like to see students get lost in these abstractions and think that this is what calculus is about. These are just tools that we put into our toolbox to allow us to solve problems quickly, but it doesn't really get to the essence of what's really going on in calculus, which is more of our first principles, the stuff over here. Hope that makes sense, and I'll see you guys in the next video.